Okay, so now we have, you can see up here on the board, by the way, that we're working on some torque problems with the physics ones. But now let's consider chapter 8 in our books as we go through solving some of those problems. And we're going to get into some of the more conceptual aspects of it as we go through, and obviously some of the math as well. But now let's consider what we have here. Going back to the beginning, the only thing I'm really not going to cover is section 8.6. I'm going to do that in class. It's reading the potential energy curve. Now, first, what I'd like to talk about here is, let's just say I have this mass right here. This is 50 gram mass, okay? And I throw it up, okay? Now, as I throw it up and it comes back down, a couple key things happen here. First of all, on the way up, okay? On the way up, gravity is applying a force down as it goes up. Now, the angle between the force and the direction of motion is 180 degrees. So on the way up, we have negative work being done. Okay? Now, it turns out that there is going to be a change in the energy as it goes up, and we account for this a little bit differently with what are called conservative forces. Okay? So now, instead of just looking at the work that's done by the force of gravity, which you can still do, remember, energy is all about accounting, and we're going to take a special accounting trick here and take into account gravity. Nothing different from what we've seen in the past, but this is the theoretical basis of why we can do what we've done. Okay? So now, work being done by gravity on the way up, okay, is negative. Now, what that means, okay, if the work on the way up is negative, we also notice, okay, from what we've talked about in the past, the potential energy is increasing, okay? Kinetic energy is decreasing on the way up. Potential energy, what we call potential energy, gravitational potential energy, is increasing. It turns out that the way that we account for this is that, and we're going to start using U, potential energy by a conservative force is equal to negative the work done by that conservative force. Okay? Well, then you say, well, what the heck is a conservative force? Well, a conservative force is a force that's, most simply put, it's a force that's reversible. Okay? When I take this mass and I throw it up and it comes back down, it has the same speed when it reaches back down into my hand again. Okay? It's showing that it's reversible. Now, if I were to take that same mass and try to slide it, let's see if I can get something that's big enough here. Okay? If I were to take the same mass and try to slide it across the well here, as it slides across, it comes to a stop. It doesn't come back and start picking up speed again. Friction is not a conservative force. It is not reversible. Now, there are more specific things that go into with what makes a conservative force and a non-conservative force. They list them here on page 168 in your text, in the Halliday and Resnick text. But for our purposes, what we're thinking of reversible forces. Now, we're going to think of two specific examples of forces that are conservative. We're going to take a look at gravitational potential energy, and we're going to look at spring potential energy. We'll also look at certain cases where we will just state that it's a conservative force, and it'll be a general force, and we'll treat it as potential energy. But for specific examples of conservative forces, gravitational potential and the spring potential are good examples. Now, going on, and the important aspect of conservative forces is that we can use potential energy, okay, this U, okay? So now, in general, we know that work is equal to, in its most general form, xi, xf, force is a vector dotted with dx. Now, we're going to look at one-dimensional, so we don't have to worry about this, about the dot product so much, other than to say if it's, we'll probably put it more in cosine, recognize whether or not it's negative or not, okay? So in other words, if the force and the direction of motion are in opposite directions, we have to recognize it and put a negative in there. So we're just going to say that this is a little bit less general, because it's not including the dot product. But we're going to say that the force is either directly in the direction of motion or opposite the direction of motion. So now, potential energy, which we said was negative the work, the potential energy, okay, really the change in potential energy in this case, I should put a delta there as well. The change in potential energy is negative the work done by that force. Okay? The change in potential energy will equal negative from your starting point to your ending point, f of x dx. Okay? It's all well and good. Okay? Let's take a look at a specific example on how we do that. So now, let's take a look at gravitational potential energy. And this is not planetary scale, this is near Earth's surface. When we get into planetary scale, then we have to start looking at how the gravitational force changes with distance. Okay, but near Earth's surface, the gravitational force is constant. So we're going to say that delta U, G, okay, for gravitational potential energy, is equal to negative, and instead of x, I'm going to call it y initial to y final, of negative mg, and it's negative because we're going to say as you increase in height, okay, as you increase in height, y is going to get larger. So if it's anything that's pointed down, has to be negative. So the gravitational force, this Fx, in this case Fy, is pointed downward. dy. Okay, and the dy is a little change, the incremental change that you have vertically. Infinitesimally small increments here. So now, one thing to notice is that mg, okay, near Earth's surface, that doesn't vary with the height. Okay, it does over significant distances, but for near Earth's surface, we don't have to take that into account. So these two negatives right here are going to cancel out. And what I can do, especially those of you in Calc 1, these two are therefore constant, and I can pull them out of the integral. Okay, and I'm left with dy. So now if I integrate dy, change in potential energy with respect to gravity, okay, is going to be mg. Okay, the integral of dy is just y. And I'm going to do that over from y initial to y final. So now I just look at, for those of you especially in Calc 1, okay, I plug in y final and I subtract off y initial. So this becomes mg y final minus y initial, which we typically would write as mg delta y. Okay? So the change in our gravitational potential energy will be mg delta y. Now, a lot of times we take into account the fact that our initial position will be at the ground. We have to set a reference. Okay, the important thing is that we set a reference, and what we have to do, and we don't do this for again planetary scale. Actually, at planetary scale, we set potential energy equal to 0 at infinity. What we're going to do here is set gravitational potential energy equal to 0 at y equals 0. Gravitational potential energy equals 0. Okay. So therefore, gravitational potential energy in general, if I can do that, would be mgy. All right, at any particular location. Now, going along with that, we have elastic potential energy. If you need a second to catch up, hit pause for a second. All right, so now we're going to move on and look at elastic potential energy. This one is a little bit more involved, proving where some of this stuff comes from. So now, let's call it spring potential energy. Okay. Now, again, the work, potential energy, change in potential energy will equal negative f of, and we're going to use x, dx in this case. Okay, we know that the force from a spring is equal to negative kx. Okay? You stretch it in one direction, it's pulling back in the other direction. You compress it this way, it's going to push back that way. So whatever direction you take it from equilibrium, okay, the force is going to pull back towards equilibrium. So force from a spring is negative kx. So my delta U will equal negative integral from x initial to x final of negative kx, and because we're doing it in terms of x, dx. So now, negative, negative again becomes positive, positive. The k is a constant, I can pull that out. So my change, and this is going to be due to a spring, will equal k integral from x initial to x final of x dx. So now, x dx, that is the integral of x dx. I'm trying to go slow for Calc 1ers. Okay. K stays out. I have 1/2 x squared. And I'm going to do that from x initial to x final. Again, okay, I'm going to substitute in x final, subtract off x initial. So when I do that, potential energy from a spring, 1/2 comes out, 1/2 k x final squared minus 1/2 k x initial squared. That's the change in the potential energy due to a spring. Now, just like we did with gravity, we want to set a reference point that's 0. Okay? We usually say equilibrium is our 0 position. So I'm going to say at x equals 0, the potential energy of a spring equals 0. If I don't define that to be 0, then I can't say that it has a certain amount of, I can't say that it has a certain potential energy number. Really, always what we're looking at is a change in potential energy. But a lot of times, for convenience sake, we want to say that the potential energy of the system is such and such number, and in order to do that, we have to set a reference point. So when we do that, we can say that the potential energy due to a spring is equal to 1/2 k x squared. Okay. So now, taking a look at some problems We're going to look at conservation of mechanical energy and then do a quick problem based on that. Okay, we're going to look at gravitational potential energy problem. So now, we know, okay, changing topics here a little bit. This will be conservation of mechanical and mech energy. So now, if we're looking at conservation of mechanical energy, okay, this is with no external forces involved. Okay, all conservative forces, no applied forces, no friction. We're just looking at conservative forces. Conservation of mechanical energy. We know that work is equal to a change in kinetic energy. Okay, I'll just call that, I've been calling it K. Okay, work is equal to a change in kinetic energy. We also know that work by a conservative force is equal to a change in potential energy, negative. Well, look at this. It's just the conservative forces that are acting. Change in kinetic energy is equal to a negative change in potential energy. When I drop something, potential energy decreases. By the same amount, the kinetic energy is increasing. Throw it up. Okay, potential energy is kinetic energy is decreasing, it's slowing down, while potential energy is increasing. Okay, so now, this is just saying whatever energy I gain here, I lose here, and vice versa. If I lose it with kinetic energy, I gain it in potential energy. Okay, that's the simplest form of conservation of energy that you will find because it's only including conservative forces. Okay, now we can rearrange this. Okay, and we can come up with our peaky. Okay, and we can say that kinetic energy, and you can do K final minus K initial is equal to negative U final, negative the quantity U final minus U initial. You do all that, we'll find that K initial plus potential energy initial is equal to K final plus potential energy final. Okay. So now, I'm going to step off camera for a second. I want to make sure that this is still in view. Okay, so now, that is the AP form of peaky. Okay, instead of calling it potential energy PE, call it U. It's a little bit more standard. You guys should learn some more of the standard as opposed to Mr. Folksisms. So we put it in those terms. Now what this is also saying is that we have a quantity called E mechanical. This will equal the kinetic energy plus the potential energy. So now, if whatever I gain here, I lose here, and vice versa, okay, this is saying that my change in mechanical energy, so long as it's only conservative forces, is equal to 0. Conservative only forces. Okay? Again, conservation of energy. So now, how does this make a difference to you or me? Let's take a look at an example. Okay? We've always looked at stuff that's just dropped or goes down a hill. Okay? It also works when you're talking about essentially a pendulum. Now, a person is right here. This is a I don't know, 5 meter rope. The person will swing down. This is still 5 meters. So now the person's right here, holding onto the rope. Okay? We want to know how fast the person's going to go when he falls down this far. Let's say that this is 20 degrees. Okay? This is a pretty common example. Now, the trick in solving this problem is figuring out how far the person falls. Okay? If you figure out how far the person falls, this becomes peaky peaky from last year, or cuckoo, I guess. Yeah, there you go, cuckoo. All right, that sounds almost as good as peaky peaky. All right, so now we want to figure out how far the person falls. Well, now, the whole distance here is 5 meters. That won't change. But let's take a look at this distance right here. If this is 5 meters from top to bottom, that's 20 degrees. This right here, this distance right here, it's going along a reference axis, or it's adjacent to the 20 degrees. Okay? This is 5 meters times the cosine of 20 degrees. Running out of room. Cosine of 20 degrees. So this distance right here, okay, is 5 meters times cosine of 20 degrees. The whole distance is still 5. So now, this distance is fine and all, but we don't want this distance, we want this distance. So if I just say that this is length L, and I'm going to put it in terms of length L because it's good to know the more general form. Okay? This will be L cosine theta. So this height that he was originally, L cosine theta, this goes down to L. You take this distance and subtract off that distance. So that delta H there is equal to L minus L cosine theta. Okay? This is kind of a big one whenever you're doing these pendulum bob problems, figure out how fast it goes. So now, in this specific case, this is going to be 5 meters minus 5 meters cosine 20 degrees. So now, my software, and I get a change of height of only 30 centimeters. I like to use 4 digits while I'm working the problem. So now, taking a look at this, okay, cuckoo, okay, K initial plus potential energy initial is equal to K final plus potential energy final. Initial kinetic energy, 0. This will be mg h, which will be the 0.3015 in this case, is equal to kinetic energy final, which is 1/2 m squared, final squared. This is 0. M's drop, so my final velocity is equal to 2gh, which is very helpful. Square root. That's very helpful for lots of these problems. The real basic conservation of energy problems, whether you're going down a hill, whether you're swinging on a vine, okay, anything where it's just gravitational potential energy, final velocity is going to be, if you start at rest, more generally be 2g delta h, but especially in this case where we set the height equal to 0 here, you can just do 2gh. So final velocity is equal to the square root of 2 times 9.8 meters per second squared times 0.3015 meters final velocity is equal to 2.43. I leave 3 digits for final answer. 2.43 meters per second. Okay. Going past potential energy curve. All right. So now we have to take a look at work done on a system by an external force. Now, I have some problems with this. Okay, the way that your book does it, the way that I do it. The book takes a look at the amount of thermal energy that's involved when you're talking about friction. If you account for the work that's done by conservative forces, be they gravity, be it springs, electric field, magnetic field, whatever, okay? You can account for potential energy within potential energy. Okay, so you don't look at necessarily the net work, where we said that before. The net work was equal to the change in kinetic energy. This is always true. That always works. There's nothing wrong with that. But we've got some shortcuts that we can do. Okay, so now we're going to take a look at the work done by non-conservative forces. Okay? Meaning applied forces, frictional forces, okay? Constant forces. All right? In those cases, we like to leave potential energy in the equation. When we do that, I'm going to call it K. I should just call it. There you go, just K. The work done by the net work done by non-conservative forces, I should say. Okay? We add up all the non-conservative forces. It will equal a change in the mechanical energy. You go, whoa, 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 Mr. Folks, you still have up on the board here, delta E mech equals 0 for conservative only forces. Okay? Don't forget caveats. Okay? Here, this is a little bit more general. The work done by